Hello, Dr. Prasad. Don't worry, you won't be seeing my face during the presentation. I just wanted to thank you for the course and for the opportunity. Honestly, I learned a lot during these two projects, and I really appreciate that. So now I'll just jump back into the presentation. This is a project that's been completed in December of 2025 as part of a course in mechatronics at the University of Maryland Eastern Shore. The project is to turn the Elegoo Smart Robot Car Kit into a follow me robot in a way that robot will follow the person, and as the person moves, the robot should maintain a certain distance, which is in this case is about 60 centimeter with the person. As part of the assumptions for the project and to make it less complicated, the arena or working area will be free of any other objects and only the target or basically the person will be in the area. This is kind of a funny way of showing different modules and functions of robot, but think of a pirate ship that should track a target. It's very similar to a robot. Now, there are different components and functions, such as the person who look far and around to find target. That is a robot sensor. Once he spots something, he let the captain know. Our sensor send data to Arduino board. The captain will use some tools and techniques to find how the ship should move. Those tools are ESP32 board and the classifier I developed, which we get into that shortly. And then the captain make the move command to the crew, which are the powertrain module of the robot. Now, back to our robot system structure. We have the Arduino board as the base. Then we have the code within the Arduino, which is to communicate with other part of the system we have. And then we have sensor, we have DC motor, and also we have ESP32 and the classification model that has been developed specifically for this application using machine learning technique and play a key role as the brain of the robot. All these parts and functions should be in complete sync, working together to make the robot perform as designed. As you see in the diagram, these components are not directly communicating, but they communicate through Arduino board. And the code within the written for this application is the language for the communication. Okay, so here we see the overall control flow diagram of our system. It will start with initiating all the elements and modules that is on the board or on this robot, such as sensor, motors, and ESP board. Then once everything is ready to go, we will have the scanning function started. So basically, we're using a servo motor that is attached to the ultrasonic sensor on the robot and rotates the sensor. As the sensor rotates, it gathers information and distance data from the environment. And then once the information is gathered in a specific way, which we'll get into that later, it will transfer the information to the Arduino for making movement decision. Arduino board send those information to ESP32 as the brain of our system. Within ESP32, we have a completely separate code that is being used to analyze the input pattern. This is the neural model classifier that has been developed and makes this robot intelligent. The classifier estimates the position of target and send a response to Arduino, which tells Arduino the position of the target relative to the robot. And then next step, Arduino will tell robot how to move. If the target estimated to be either to the left or right of the robot, Arduino will make a command to the DC motors to spin the robot toward target, either with a slow or fast spin, depending on the estimated position of the target. Once robot turns, it will go back to gather a new set of distance data to see whether or not robot has turned enough toward target. If the target is almost in front of the robot, so let's say in the center, then the Arduino will make command to move forward or backward depending on the distance from target. And then during forward or backward movement, robot, or I should say the sensor on the robot, will constantly measure the distance on to the target and then send it back to Arduino to adjust the speed of the robot, and then and also stop the robot once the robot gets within the desired distance from the target. And then again, robots starts the search or data gathering cycle. As you see in the diagram, there are two areas that data can be transmitted for visualization and system analysis. The idea is that data should be transmitted over the Wi-Fi, which is a capability that can be built into the ESP32 board. And with that, the user or the developer should be able to monitor and analyze the response of the code and the system, and be able to improve that based on the analysis. Okay. Now that we reviewed the entire control flow of the robot, here I'm explaining a little bit more about the sensing module. So our sensing module includes two components, an ultrasonic sensor and a servo motor. The reason to use servo motor is that the ultrasonic sensor has a very narrow field of view, which is only about 15 degrees, and not enough for our project. Therefore, to expand the field of view of our or scanning range, basically, we're using a servo motor to rotate the sensor. But during the calibration, I noticed that when sensor is right aligned with the heading axis of the robot, the servo is at 85 degree of its own moving range. So everything has been set and developed based on the fact that the middle of the range is when servo is at 85 degree. So as it shows in the picture, by using the servo motor, we're going to expand our scanning area. And in this case, servo is rotating from 25 degree to 245 degrees. So it is about 115 degree of rotation, which gives us about 135 degree of a scanning area, which is pretty good for this application. And as sensor moves within the range, it will pick up distance data point every about 7 degrees. So overall, at each cycle, we'll have 19 data points that is being collected and will be analyzed in the system, which I'll get into that in a second. Once sensor captures some data points, we should be able to use those data points to tell if target is present, and also the position of the target relative to the robot, whether to the left side or right. Does the robot need to turn slightly, or more rotation is needed? However, with the raw data that comes out of ultrasonic sensor, the with that raw data that comes out of the ultrasonic sensor, it is not possible, or I should say, easy to make a good judgment. So to overcome this limitation, I used a machine learning technique to develop a neural model classifier that can receive data sets from the sensor and tell where that target is relative to the robot, which is what we really need to track the target. As you see in the picture on the left-hand side, uh, I basically made some sort of a meshed area to collect several sets of data point at different positions and distances. And I used those data points to train a model. And as you see in the middle of the page, after training the model, the accuracy of the model is about 90%, which is pretty good to start. Also, in the image on the right-hand side, you see that the pattern that the classifier has developed to predict the position of the targets when sensor sends a new data set at each sweep. So what we have is basically a tool that receives sensor data and or sensor data sets and tell the position of target in the form of far left, left, center, right, and far right with a high accuracy, relatively high accuracy, which is needed for our robot movement. Some benefits of utilizing this approach can be basically improving robustness of the system against noise and ambiguous measurements. Also, we made clean separation between different modules, which allows independent updates to each module without changing or touching other modules. Last but not least, we are adding a level of intelligence to a robot that can be improved in future. As last comment, um, I'd like to point out and reflect on some items I noticed after reviewing the test results. There are some areas that needs to be improved, such as discrete turn cycles, and the fact that the classifier needs to be trained with more data points to be more accurate and reliable. Also, ultrasonic sensors are sensitive to noise, which limits the performance of the robot. Therefore, there are some improvement ideas that should be considered for next generation of this robot. One of the critical features is telemetry and logging system performance. As of now, all the hardware and software to make that happen has been developed. However, it needs the final debugging and validation tests. Another feature is to add the camera on the robot to work in conjunction with ultrasonic sensor to improve tracking reliability. Also, by adding confidence gating on accepting classifier outputs and filtering distance data, as well as using PID and acceleration limits to control the velocity of the robot, the performance of the robot will increase drastically and can be turned into the next level of intelligent robots. That's it for me, and please do not hesitate to let me know if you have any comment or any idea that can be applied to this project. I'll be happy to hear all the comments. Thanks.